Okay, thanks everyone for being here. Yes, my name is Dang Song. I'm a professor at UC Berkeley and also the founder of Oasis Labs. So today we'll talk about actually a new optimistic rollup. And so scaling blockchains with the EVM-native interactive file proofs. And the work is supported by the new blockchain Web3 center at Berkeley called the Berkeley RDI. You can go to rdi.berkeley.edu to see more details. And this is joint work with my students, Ju and Ujwa. Okay, so as we all know, today's Ethereum architecture really doesn't scale. I don't need to go into that more. And also because of that, there has been proposals for rollups as a scaling solution. And it's also called validating bridges. Essentially, with the rollup, you commit the transaction data into the layer 1 blockchain, but you offload transaction execution to essentially layer 2. And the important part is how do you ensure on layer 1 that the off-chain execution is actually done correctly. So you want to essentially checkpoint the off-chain execution state on-chain as assertions. And for rollups, there are mainly two types, as many of you here probably are familiar with. The one is validity proof using, for example, zk knowledge proofs. And the other type is fraud proof, also called optimistic rollup, where essentially you have asserters or executors that actually commit their assertions on chain. And then you can have challengers who can challenge on chain if they detect that the committed assertions are incorrect. And in today's talk, we'll particularly focus on optimistic rollup. I won't go into the details how validity proof and fraud proof, their pros and cons. So in this talk, we'll just focus on optimistic rollups, ORUs. So very quick in terms of optimistic rollup, I already mentioned. So essentially, there are different roles in optimistic rollup. You have the sequencers that actually commit the order transactions on chain. And then you have these executors that executes transactions off chain, and then they commit assertions on chain. And you have a verifier on chain that when a challenger detects that a committed assertion is incorrect, they will perform a challenge on chain. And on chain, you have a verifier to verify whether this challenge is correct. And in particular here, for the executor, when they execute transactions off-chain, usually they execute it in what we call off-chain VM. Here we call it ORU VM. So that's the key for fraud proof. And essentially, the key point is that on challenge, the on-chain verifier needs to be able to verify the validity of the state transition in the ORU VM. And there are different types of optimistic rollups, including non-interactive, where when an assertion is being challenged, the asserter and the challenger doesn't need interactions. Essentially, the verifier on chain will be able to actually verify the state transition of the entire assertion. And the other type is interactive, where during challenge, the asserter and the challenger needs to have interactions to be able to essentially enable the verifier to verify the challenge. So, just very briefly, the ORU with non-interactive fraud proof. This was first done by Optimism version 1, and in particular, in this case, they introduced a VM called the OVM. Essentially, it's a modified EVM running on EVM. And on challenge, it tries to execute the entire transaction on chain to validate the state transition. And as we all know, there has been many problems with this approach. Simulating an EVM on EVM is very costly and error-prone, and it causes poor compatibility with EVM, including, for example, you have to replace certain opcodes by contract calls, and that puts in various limitations in terms of what the L2 contracts can do, and also the size of the transactions and so on. And also, the OVM is very complicated. It's hard to audit and maintain. Because of that, people realized this approach is very challenging. So in general, the entire space has been moving to the interactive ORU instead. So with interactive, so instead of trying to, for example, simulate the whole state transition of the entire assertion on chain, instead you have a challenge between the asserter and the challenger. And through this bisection protocol, which is a multi-round protocol, the challenger and asserter together can narrow down essentially a single instruction that needs to be validated by the on-chain verifier to figure out who is correct, who is wrong. And this approach has a lot of challenges over non-interactive approach. And also in this talk, we'll focus on ORU with interactive fraud proof. So when we look at ORU with interactive fraud proof, again, there are actually several generations. So the first generation is what we call EVM compatible ORU. So in this case, the ORU VM is a custom VM with an EVM emulation layer so that you can run existing Solidity smart contracts on this ORU VM to execute. So in this setting, the underlying essentially the clients, the Ethereum client implementation is is done by a custom VM, and and the EVM compatibility is by this emulating layer that emulates EVM inside this custom VM. And in this case, the one-step proof, and also you'll see in this talk, we mainly focus on this one-step proof process. So in this case, the one-step proof is generated on the custom VM instruction level. So the example here is Arbitrum-1 that developed the first EVM-compatible ORU with the interactive fraud proof. So essentially, they built a custom VM called the Arbitrum VM AVM that uses that to generate one-step proof. So when we look at this approach, it has a number of challenges. So first of all, this custom VM actually has many security challenges. So for example, the re-implemented EVM on custom VM could drift from Ethereum specification, and it's very difficult to audit and maintain this. And also there are many compatibility problems for developers as well. So for example, it provides limited compatibility with existing smart contracts. So for example, Arbitrum-1 doesn't support a number of pre-compiles, and also it has limited compatibility with existing Ethereum toolchain and ecosystem. Right. And also another important, some of the other important issues with this type of approach is that it's challenging to audit and maintain a custom VM for EVM compatibility. So in this case, you actually have a very large, complex trusted computing base. So essentially, the whole EVM emulation layer and the custom VM one-step proof generator, all these are actually part of the TCB to ensure the correct execution of the custom VM, and also to enforce Ethereum semantics. And in general, because of the large TCB, it's hard to maintain and upgrade. And it has to re-implement a lot of the tooling that has already been implemented in existing Ethereum clients. And also a very important aspect also is that the on-chain verifier in this case actually has no knowledge of Ethereum specification or semantics. It's only verifying that the AVM instructions has been executed correctly. Right. Okay. So one thing I want to point out here is the Ethereum semantics, and you'll see later on in the talk why this is particularly important. So when we talk about Ethereum semantics, it essentially is the state transition rules that have been specified for Ethereum for state transitions across transactions, and this includes multiple components, and one part is intra-transaction semantics. So essentially the semantics of the EVM opcodes. And also another component is inter-transaction semantics, including transaction initiation and finalization, including things like purchase and refund gas, error handling, and so on. So really, when we look at rollups, the key here is that we want to ensure that when you execute these smart contracts, Solidity smart contracts on L2, you want to ensure that in the end, you can, through this the on-chain verifier, you can ensure that the execution of the smart contracts essentially follows the Ethereum specification. That's really the goal for L2 and for ensuring the security of L2. And because of that, essentially the ORU VM needs to implement Ethereum specification. And right. So however, for the EVM, and also the on-chain verifier needs to be able to enforce Ethereum specification. However, as we can see with the EVM compatible RU with this approach, unfortunately, actually does not handle this. So the on-chain verifier in this case only enforces the correctness of the execution of the custom VM blindly. Actually, in this case, doesn't know the on-chain verifier doesn't know the Ethereum specification directly at all. So due to the various challenges in the EVM compatible ORU, so the community has moved to essentially generation 2, that's called the EVM equivalent ORU. So the idea of the EVM equivalent ORU is to actually try to reuse existing Ethereum clients and then use that to build the L2 client. And in particular, in this case, the ORU VM here utilizes existing Ethereum clients, but it wants to still be able to do efficient fraud-proof generation and verification. And in order to do that, so currently, approach taken by Arbitrum and Optimism is to compile existing EVM Ethereum clients down into a custom ISA to then do the one-step proof using the custom ISA. So in this case, for example, Arbitrum Nitro compiles GetCore down to WASM, and Optimism has proposed to compile the Ethereum clients down to MIPS. So this is a second generation approach, EVM equivalent ORU. But however, we'll see that this class of approach also has many challenges and many problems. One is that the on-chain verifier, in this case, also is unaware of Ethereum specification. It only checks for correctness of execution of the off-chain client program. And because of that, essentially it leads to large, complex TCB and does not support ORU client diversity, and has a poor upgrade transparency, and also requires frequent on-chain upgrades, even when the underlying Ethereum specification does not change. So let's now go into each one of these in a little bit more detail. So first, so I explained what Ethereum semantics is earlier. So the first problem for this type of approach is that really the on-chain verifier actually has no idea, has no knowledge of Ethereum specification. All it does is to check for the correctness of execution of an off-chain client program. But it actually doesn't know whether this off-chain client program follows the Ethereum specification at all. And right. So instead, the on-chain verifier actually has a hash of the client program code, and the on-chain verifier essentially checks whether that program has been correctly executed off-chain. So the problem for that is that it actually leads to a large TCB for the rollup. So a TCB of the ORU fraud-proof design is essentially the security critical code base that is required to ensure the compliance with the Ethereum specification. So what is the TCB in these EVM equivalent ORU? So because the on-chain verifier does not know the semantics of Ethereum, and it's only checking for the correctness of the execution of the off-chain client, L2 client. So in this case, essentially, the whole TCB includes, besides the on-chain verifier and so on, also includes essentially the entire off-chain client, because essentially it needs to assume that the off-chain L2 client actually implements correctly the Ethereum semantics. And hence, the TCP is really large. In this case, includes the off-chain Ethereum client and also the whole compiler toolchain that compiles from the Ethereum client down to with the custom ISA. So this is just a picture illustrating the large TCP of the EVM equivalent RIO, which basically includes everything, both the on-chain verifier piece and the on-chain commitments of the off-chain clients, and also the whole off-chain client and the toolchain for compilation. And because of this, also there's then this also leads to other issues. One issue is the lack of client diversity. So let's look at what we mean by optimistic rollup client diversity. So the goal here is that ideally for client to enable client diversity, you want to ensure that you can have different clients that actually participate in the challenge protocol in a permissionless manner. Okay, so I have to go faster. That there's a lot to talk through. But because of this, the optimistic with this approach, it actually doesn't support client diversity because the on-chain verifier can only verify the correctness of the execution of the particular client. And also it leads to issues with the on-chain verifier upgrade. So because in this case, the TCP is so large, so anything that changes in the off-chain client and also in the compilation toolchain will require on-chain verifier upgrade. And also it lacks upgrade transparency. Because now when anything in the client and also in the compilation toolchain changes, you actually, because it's part of the TCP, you have to investigate the upgrade to audit the upgrade. So it really lacks upgrade transparency, and also it causes unnecessarily frequent upgrades because again, anything that changes inside the entire the off-chain client and also the compilation toolchain will result in you need to actually upgrade the on-chain verifier part as well. So then what is the ideal ORU? So then the ideal ORU is that, so of course it needs to be functional, meaning we want to be efficient during normal execution and the dispute resolution. And also it needs to be fully compatible with Ethereum and its ecosystem to be able to run existing smart contracts and support the tooling and so on. And you really wanted to have minimum TCP and to be able to support the client diversity and to be simple to audit and maintain and upgrade. So with this, we propose a new approach for optimistic rollup that we call EVM-native ORU. And really, the goal here is that in order to achieve the goals that I mentioned, what we want is that, number one, we want the on-chain verifier to actually be aware of Ethereum semantics. And more specifically, we want the on-chain verifier to actually be able to enforce exactly the Ethereum semantics, nothing more and nothing less. And what this leads to is essentially an EVM-native ORU, where we actually want to generate the one-step proof directly at the EVM opcode level. With that, and with the on-chain verifier that exactly enforces Ethereum semantics, it can enable this new type of ORU, EVM-native ORU, that gives us all the advantages that I mentioned in the earlier slide. So with this, essentially, it's pretty simple. We essentially reuse existing Ethereum clients, for example, GET and so on, and then we directly generate a one-step proof at the EVM opcode level. So this way, it has the advantages that it has a minimum TCP. So in this case, unlike previous approaches, where you have the TCP that includes the whole off-chain components and compilation toolchain, in this case, we really have the minimum TCP, which is only the on-chain proof, one-step proof verifier. And And also because the one-step proof verifier directly verifies and enforces Ethereum semantics, nothing more, nothing less. So the TCP here is optimal. It's a minimum. And also because of this, it supports client diversity in a maximum way. In this case, any Ethereum client that follows Ethereum semantics will be able to be a client that performs challenges and so on. So it really supports client diversity in a maximum manner. And also in this way, it supports much better upgrade transparency. You only need to upgrade when the underlying Ethereum semantics changes, and the upgrades will only be, so you only need to verify the on-chain verifier that actually has the changes due to the underlying Ethereum semantics upgrade. And also you have much lower upgrade frequency because you only need to upgrade when the underlying Ethereum semantics changes. So with this, we have built the first EVM-native ORU called a Specular. So Specular also has a modular architecture design, and the current reference implementation is built on Get, and we have minimal changes in Get, which actually altogether include less than 100 lines of code of Get. And so we hope that these changes can actually upstream to Get, so that every Get client in the future with these changes can be rollup aware and can support rollups. And in addition to those changes, essentially we have these modular modules, including proof generation modules, rollup modules, and then on the Specular bridge we have the one-step proof verifier that I mentioned. So given the interest of time, I won't actually go into the details. So as I mentioned, right, so the changes to the Get is really small. And so just very briefly, essentially, the key of this design is the one-step proof, how we actually build the one-step proof, and also enable one-step proof at the EVM opcode level directly. And also I wanted to mention is that this approach also has a number of side benefits, because now the on-chain verifier essentially is a specification of Ethereum semantics. And this specification alone actually has many benefits. It can be used to actually for testing new Ethereum clients implementations. And also, right, so that specification itself is actually very meaningful, very useful as well. So I won't go in, due to time limit, I won't go into the details of how we generate the one-step proof and that's the one-step verification. And the system is actually up and running currently, and you can actually do the fraud proof generation and verification today. And it's very efficient as well. So again, given the interest of time, I won't go through these comparisons, but hopefully the talk has shown you the advantages of this approach, the EVM-native ORU advantage over the others. And also, I won't have time to talk about the future work. There's a number of future work directions that we want to explore. But one thing, just 1 minute, I wanted to only briefly talk about this is one of the future work we want to explore is the modular architecture that supports a spectrum of challenge policies. So far in Optimistic Rollups, it's an open challenge, anyone can challenge, but it has a number of disadvantages. So Oasis actually is the first modular blockchain architecture that proposed separating execution from consensus 4 years ago, and it's actually the first, now the term is called insurance rollup. So basically it has the rollup built into the consensus layer, and it actually uses a different way called the discrepancy detection for the challenge. And with the Specular, we're also interested in exploring this overall space, design space of how you actually do the challenge policy. Essentially, it's a broad spectrum. You can do open challenge, or you can do this explicit discrepancy detection, as what Oasis protocol proposed, or you can actually do a blend of the two. You can do both open challenge and explicit discrepancy detection, which has a number of advantages. And again, due to time limit, I won't have time to go into it. So I recommend you to go check out the work, here's a website, specular.network, and you can go go to the process and then try out our applications deployed on L2 today. It's running on testnet today. You can try out the EMM. And thanks to Pierre for helping with development and deployment as well. So